Hi, I'm Dean Newman. What follows is a recording of a talk I gave recently on software development for safety critical systems, with a particular focus on whether some common branching models are appropriate for critical system development. I'm not a YouTube creator, and I'm not going to ask you to like or subscribe. I posted it in the hope that some people would find it informative.
Thank you, Vivian. That was a very kind introduction. Hello, everyone. Thanks for joining. I see statements like this made in online forums from time to time. So what do you guys think? Is this statement true? Well, it turns out that the answer to that has something to do with safety critical software. Today, I'll give you a glimpse into the development of safety critical software, why it's different from other software development, the different roles involved in its development, and how some things that are considered best practice for consumer software would be unacceptable in a safety critical project. I'm going to spend a fair amount of time on Gitflow and trunk-based development, but I have to take you on a journey first before we get there, because without the right context for that discussion, I wouldn't be able to make the points that I'm trying to make. My name is Dean Newman. I'm a licensed software engineer. So what exactly does that mean? Software can be graded according to the level of risk to its users if the software malfunctions. Consumer-grade software is your standard B2C stuff, web applications, mobile apps, development tools. In consumer-grade software, a fault in the software just inconveniences the user. There's no risk of harm. And at this grade, there's usually no service level objectives either. One step up from that, enterprise-grade software is software that a company uses to automate its business processes. So a fault in enterprise-grade software would impact the business's ability to operate. At this grade, you typically do see service level objectives. Another step up and you get carrier-grade software. A carrier is a utility or telecoms company that provides a regulated service to the public. Carrier-grade software, then, is software that is used by a carrier to provide that service to the public. So a fault in carrier-grade software impacts more than just the business. It impacts the public, but with no risk of harm. At this grade, you see service-level agreements written into contracts that specify a maximum allowable downtime per year and a maximum allowable time to restore service if the software has a failure. And this is where you start to see bug tracking workflows that have clocks and time limits for providing a workaround and a resolution. One more level up, and you get to regulated engineering work. Safety critical software is an example of a regulated engineering work. At this grade, a fault in the software carries a risk of harm to the public. At this level, you're beyond SLAs. In order to release the product, you need approval from a regulatory body. And to get approval, you're required to provide proof that you followed strict standards during its development. And the result is that a product that you assert is safe for its intended use. That proof is called a safety case. And that's the line of demarcation. The law in Canada says that the development of software that carries a risk of harm to the public must be performed or directly supervised by a licensed software engineer. Below that line, software which does not pose any risk of harm can be developed by any software developer. So that's the legal distinction between a software engineer and a software developer in Canada. And that's the first difference that you're going to see when you develop safety critical software. There's an additional role defined. Software developers can work on those projects, but only under the direct supervision of a software engineer. What's interesting to note in the wording of the law is that safety critical software isn't the only regulated engineering work. Harm to the public includes harm to life and health, but also harm to property, harm to economic interests, harm to the public welfare, and harm to the environment. The role of the software engineer is to take responsibility for ensuring that the entire software development lifecycle is performed in accordance with standards of professional practice. That person is called the engineer of record for the project. The engineer of record is the one that has to sign it and seal it when you submit the safety case for approval. There are several different industry-specific standards prescribing what you must do during the development of safety-critical software, and there will be one of those standards that applies to your project, depending on the industry that it's for. But these standards are all 90% the same. The reason there are differences is because there are different levels of risk in different industries. A software fault in a medical device could kill its user, while a software fault in a car could kill everyone in the car, so multiple people. A software fault in an airplane could kill hundreds of people, and a software fault in a nuclear power plant could kill millions. The higher the level of risk, the more strict they get. Even within a single industry, though, software can have different levels of risk depending on its intended use. Safety integrity level 1 is for any system that carries a risk of harm to property, and those must be designed to have a probability of failure of less than one failure in 100,000 hours of continuous use. Safety integrity level 2 is for any system that carries a risk of harm to a person, and those must have a probability of failure of less than one failure in 1,000,000 hours of continuous use. Safety integrity level 3 is for any system that carries a risk to the life of multiple persons, and those must have a probability of failure of less than 1 in 10 million hours of continuous use. And finally, level 4 is for any system that carries a risk of mass casualties, and those must have a probability of failure of less than one failure in 100 million hours of continuous use. That's over 11,000 years. So before you even start developing your software, you'll already know which safety integrity level you're going to have to meet, and therefore its probability of failure over time. Obviously, to meet that kind of reliability, you have to create software designs that are tolerant to the presence of defects. And you're also going to have to write code in a way that minimizes the number of defects in the code. So let's look at some defect density numbers. An analysis of over 10 million lines of open source code was done in 2017, and it found that the mean defect density of open source code is 7.28 defects per 1,000 lines of code. And the worst of it went all the way up to 42.8 defects per 1,000 lines of code. In comparison, NASA's space shuttle software was 430,000 lines of code, and it had one defect. That's 0.002 defects per 1,000 lines of code. So the way we develop open source software produces, on average, over 3,000 times as many bugs as the way NASA develops safety-critical software. When you deploy safety-critical software, it's always as part of a safety-critical system, and that system can have a very long lifespan. So the standards that govern its development cover its entire life cycle from cradle to grave. It all starts with the elicitation of requirements. And I don't just mean user stories. I mean you have to identify any safety hazards that arise based on a study of the functional requirements, and then derive safety requirements to mitigate those safety hazards. Then you have to come up with a software architecture and design that meets all those safety requirements. And once you know what you're supposed to build, then the software developers can write the code. And it's at that point that you start finding that there's problems with Gitflow and trunk-based development and with CI and CD. Then there's a whole whack of stuff you have to do during verification in order to prove that the software really does implement all those safety requirements. And you can't demonstrate the safety requirements are met like features at a sprint review. You need verification that goes way beyond unit and integration test pipelines. Then, after the system is released, you've got ongoing maintenance challenges, and then eventually decommissioning the system. All these processes must be done with formal artifacts generated for each process. That's non-negotiable. So let's talk about what development methodology you would use to do this. It's not Agile. Agile is about minimizing strict process and formal documentation in favor of collaborating with the customer to iteratively define the requirements through the delivery of software in increments. In Agile, instead of iterating through versions of a requirement spec, you iterate with multiple releases of software. The AAMI, which is an industry association for medical device manufacturers, published a technical report which tries to map Agile into their safety standard. It basically says you can be Agile if you want to in adapting to changing user requirements, but you can't do it by releasing software incrementally. It says before you release anything, you definitely need to show all the documentation as evidence that you identified, analyzed, designed, implemented, verified, and proved that you developed a product that meets the safety requirements and reliability for its intended safety integrity level. So if not Agile, then what does a safety-critical software development methodology look like? The methodology most often cited in safety standards is called the V model. It's like a waterfall model folded in half. Every artifact is derived from something and gets verified against what it was derived from. That's traceability. And Agile, because it frowns on formal documentation, is not very good for traceability. Agile is good for delivering incremental functionality faster, but it's not best practice for producing the safest software, as evidenced by those defect density numbers. Safety-critical software projects spend a lot more time in requirements analysis, deriving the safety requirements from the functional requirements. So let's take a look at that. Safety requirements are often defined in terms of shall not. A user requirement might be that an airplane has retractable landing gear. The safety requirement that you derive from that is that the software shall not allow the landing gear to be raised while the plane is sitting on the ground. That analysis of the safety hazards from all the functional requirements determines the design of the software. Mitigation of a safety hazard means anything that you design into your system to detect the hazard, avoid the hazard, minimize the damage of an accident, or recover from a hazard or an accident. Now, not all hazards need mitigation or can be mitigated. Some risks are classified as tolerable, and some are unavoidable. Those become the system's residual risks. Residual risks are what determine the system's probability of failure. So you have to analyze their combined probability of occurrence using something called fault tree analysis. The hazard register is where you capture safety requirements that you identify as you analyze the functional requirements. You could use a spreadsheet to serve as a hazard register, but you can also use system engineering software. Either way, each safety hazard that you identify, you enter into the hazard register with a reference back to the functional requirement that it relates to. And then you have to determine the degree of risk associated with that hazard. The degree of risk is determined by its probability of occurrence and the severity of harm caused by an occurrence. And the degree of risk dictates the extent you have to go to mitigate that hazard in the system. Each of those mitigations is entered into the hazard registry and becomes a separate safety requirement that the design then has to meet. And remember, mitigation includes detection, avoidance, recovery, and minimizing damage. So there's going to be safety requirements around observability, fault tolerance, fault isolation, forced restarts, etc. So once you have a complete hazard register, you have traceability from the functional requirements to the safety requirements. And that traceability is required to build your safety case. Okay, so you've defined your safety requirements, and now you need to define a software architecture that can satisfy them. If the system is complex, you'll want to use a system engineering tool to help you develop the architecture using a design language. System engineering tools are like an IDE that works at the component level. Using a tool lets you define component interfaces and behaviors, and define the interactions and communication between elements, and to execute the model. Now, the standards don't say that you need to use a tool, but they do say that you need to show traceability, from requirements to architecture to design. If you use a tool, of course, it'll help you show traceability, but tools can also generate code, and they can import code back into the model. So when you start coding the design, you're not starting from scratch. But not only do you need to validate that the architecture leads to a design which meets the requirements, you need to generate an artifact that presents evidence that it does. Evidence that you then include in your safety case. So how do you go about mitigating a safety hazard? The usual way is to design safety interlocks into your system. For example, my wife's car has a push button to start the engine. But pushing the button won't start the engine unless the electronic key is in close proximity. And it also won't start the engine if the transmission isn't in park. And it won't start the engine if your foot isn't pressing down on the brake pedal. 3 separate interlocks between different systems. Safety interlocks usually involve different independent systems or different subsystems. That means they're hard to unit test. In order to unit test the function that responds to the engine start push button, you have to mock the braking system, mock the transmission, and mock the key. And they're also hard to integration test. If a safety requirement says shall not allow, that means under any circumstance. So during integration testing, you're going to have to generate every kind of circumstance. That means you have to write tests that control the hardware to inject faults and make sure the system either handles those faults or fails in a safe way. And finally, having designed all these safety interlocks into the software, you have to make sure that for the next 10 or 20 years, no subsequent change circumvents those interlocks. So that's why after the architecture and design artifacts are signed and sealed by the software engineer, any subsequent changes have to go through a change control board. Those industry-specific safety standards also constrain your design by imposing their own requirements. The automotive and medical safety standards both stipulate that the design must include a design-safe state, and that the system must enter that state upon encountering any unrecoverable error. And they stipulate that if the system can't enter the safe state within a defined time limit, there shall be an emergency operation that can force the system into a safe state. These imposed requirements mean you can't just write a test to measure the time taken to enter the safe state. Its worst case performance has to be profiled with cycle counts in an emulator so that you can show that the design constraint is met in the worst case, by design. Also remember, this safety-critical software could be a distributed system. So entering the safe state might involve coordinating software running on several processors. That brings state synchronization and race conditions and deadlocks all into the picture. The standards say this stuff is mandatory. You're not allowed to release software without evidence that your design achieves this. The safety case that you have to submit for approval has to provide evidence that the system meets the minimum probability of failure for its safety integrity level. So now that you've done the design, you're ready to calculate its probability of failure. After you created your hazard register, you knew the system's residual risks. Those were the hazards that you did not avoid, control, or recover from. Those are the system's fault conditions. So now you have to create a combinatorial tree of how those fault conditions can combine to lead to a system failure. And you have to calculate their combined probability of occurrence. That's called fault tree analysis. The ways that the system could fail were identified during the requirements process, but their probability of occurrence isn't known until you've gone through your design process and figured out all the fault tolerance and redundancy and component lifetimes. So after you know those things, you enter the fault conditions and their individual failure rates into the fault tree analysis software, and it calculates the combined probabilities. And that's how you demonstrate in the safety case that the system meets the minimum probability of failure specified for that safety integrity level. Before we go on and talk about the actual coding process, I have an example to share with you that relates to hazard mitigation. The Boeing 737 MAX airplane was grounded by the FAA after 2 fatal crashes. The 737 MAX has a software system called the Maneuvering Characteristics Augmentation System, MCAS. The MCAS software reads data from angle of attack sensors, determines if the plane is in such a steep angle of attack that it's about to stall, and if so, it swivels the horizontal stabilizer to push the nose back down. The direct cause of the 2 fatal crashes was that the software pushed the planes into a nosedive based on data coming from a faulty sensor, even though the airplane has 2 sensors. The root cause was a failure to mitigate the hazard of a single sensor failure, along with contributing factors like pilots weren't told that this software even existed, and even if they did know, there wasn't any way for them to turn it off, which was also a failure in hazard mitigation. The fix mandated by the FAA was to prevent the MCAS software activating unless both sensors gave similar values, and to eliminate the software's ability to activate repeatedly, and to allow pilots to override the software with a kill switch. 3 separate safety interlocks. 346 people died as a result of inadequate hazard mitigation in the requirements elicitation process. That mistake cost Boeing $2.5 billion. Okay, let's move on. Once you have the software modules specified, you're done with design. So you can start writing code and the unit tests. But the safety standards also have something to say about how you write your code. First of all, as you write the code and the tests, you have to be able to show traceability of both the code and the unit tests back to the module specification that they're both derived from. So yeah, test-driven development. By the way, a common way to get that traceability is by creating a Git hook that enforces the inclusion of a Jira ticket number into every commit message, so that every commit can be traced back to its Jira ticket, and every ticket has a reference to the module spec. That's not hard to do. The standards also have something to say about the use of third-party code. Safety-critical software can use third-party code. That's allowed. However, there are strict rules. Third-party code can be classified as being either safety certified by the vendor. That's where the vendor has certified the software to a specific safety integrity level. Examples of that would be like VxWorks or QNX. Or the third-party code can be classified as a safety element out of context. That's where the vendor provides evidence that the component was developed to be capable of complying with certain safety standards at certain safety integrity levels. To use that kind of code, you include all the vendor's documentation with your safety case, and you make an argument that it complies with the specific standard and safety integrity level that you're going for. Or the third-party code can be classified as software of unknown provenance. This means you have no evidence whatsoever that the software was developed in compliance with any safety standard. And that covers pretty much all open source code. In order to use software of unknown provenance, you have to take responsibility for that code yourself and create the evidence for it being appropriate for use at the safety integrity level you're going for. At minimum, that means you have to review the known bugs list of the software you want to use and all its transitive dependencies, and create an impact analysis to determine if any of those bugs could affect the safety of your system. And you have to do that every time you update your dependencies. Some safety standards go further and also require that if you're going for level 3 or higher, then you also have to design a mechanism for detecting failures of the third-party software and protecting the system from those failures. I'm not sure how you would even do that. But the amount of third-party code that's available for you to use is probably a lot less than you think. Because when you use open source in your application, it's going to run in the cloud. And it's going to run on Xeon processors that cost hundreds of dollars and have gigabytes of RAM. But the target environment for safety critical code is a hardware device. It could even be a hardware device with a $5 processor running at 80 megahertz. So there's probably not going to be a general purpose OS on that device. If you're lucky, you might have a small real-time OS. Otherwise, your code will be running on bare metal with no operating system at all. With or without an OS, the target environment for safety-critical software might have no file system, no memory management, no separate address spaces for processes, no POSIX interface. So even if you were allowed to use it, there's pretty much no open source code that would even compile for that kind of environment. So we're really just talking about commercial code specially made to run in this environment. That's option 1 or option 2. Or open source code provided by the chip vendors themselves, like a hardware abstraction layer. That's option 3. But you're definitely not going to get a lot of your code from GitHub. You've got to write it. As you write your code, the safety standards specify that a coding standard shall be enforced. Now, in your teams, you probably created your own coding standards. And your coding standards probably talk about white space and camel case and where you like to put curly braces. But that's a coding style. Coding standards for safety critical software talk about restricting what you're allowed to do in order to make the software safer. And you don't get to create your own. The most widely specified coding standard for safety critical software is called MISRA-C. It's used for safety-critical code in automotive, aerospace, telecom, medical, defense, and railway systems. NASA's coding standards that made that space shuttle software and the Joint Strike Fighter coding standards are based on MISRA-C. And MISRA doesn't care about your style. It's all about restricting the use of constructs that make your code more likely to have bugs. If you thought that getting rid of lint warnings was hard, then you're in for a shock. Everything that's a lint warning is a MISRA error. But MISRA goes way further than that. The latest version of MISRA-C has over 140 rules, and most of them are mandatory, no exceptions. Like, you can't write if statements that have side effects. You have to assign the return value of every function call to a variable, and then test the value of the variable. That would drive Java programmers crazy. You can't have loops and conditionals with a single statement. You need to put braces around every one, even if there's only one statement in it. That way, there's no chance of Python programmers thinking that indentation level defines what code gets executed inside the loop. You can't allocate memory. You have to be able to look at the link map and see the memory address where the linker places every variable. That way there's no chance of ever having a memory leak, or heap fragmentation, or of referencing memory that's already been deleted. You can't leave commented out code or unreachable code in your program. If you like putting trace statements in your code for debugging, you can't just comment them out. You have to delete them. And you can't leave unreachable code in your program. That flies in the face of trunk-based development, where they advocate pushing code into production one commit at a time and just surrounding the unfinished feature with a feature flag to make the code unreachable. MISRA doesn't allow that. That code has to be deleted. It goes further. You can't use pointer arithmetic, unions, signals, or even many of the function in standard lib, either because they're error-prone or because they're not standard. They're implementation dependent. Getting your code to be MISRA compliant is a pain in the ass, and you have to prove that it's compliant. So if you've been relying on peer reviewers to enforce your coding standards, this would drive them crazy. The only sane thing to do is use a static analyzer that'll tell you if the code is MISRA compliant. Okay, the title of the talk says Gitflow's Fatal Flaw. And I bet you've seen that a lot lately. Everyone and his dog are telling you that Gitflow is out, branching is bad, real programmers commit directly to master. Even pull requests are out of fashion now. DZone's continuous delivery cheat sheet calls peer review an anti-pattern and says, not only should you not branch, you shouldn't even review code anymore. It says developers should just lint their code, commit directly to master, and if it passes the test pipeline, push it straight to production. Well, I've got opinions on that, but I don't want to wade into any religious wars here. I'll restrict myself to just discussing whether trunk-based development and Gitflow are suitable for safety-critical development. So let's look at trunk-based first. As I said before, safety-critical software almost always runs on devices, not in the cloud. And the software on those devices has to be supported for many years. Now, trunk-based development, as you know, is the practice of not using branches at all. Instead, all developers commit directly onto the master branch that you release from. Advocates of this claim that this is better because it eliminates the possibility of merge conflicts when doing feature branch merges, and that it gets your code into other developers' hands earlier. Continuous integration. Okay, that argument works for cloud-based software because there's only ever one version of software in production, and you control it, meaning that all bugs are fixed forward. Now, even if our safety-critical software was intended to run in the cloud, we still couldn't use trunk-based development. Because as I said, wrapping individual commits in a feature flag to make that code unreachable until the feature is finished is a violation of MISRA. But that's not our problem, because safety-critical code generally doesn't run in the cloud. It's embedded. Our problem is that for safety-critical software, you're going to end up supporting many different releases running on different versions of hardware. And you're going to have to patch those releases for many years. Now, to their credit, the trunk-based development guys do tell you that if you have to support multiple software versions, then yeah, you're going to need multiple release branches. And that means you're going to have to cherry pick commits from one release branch to another, which you never have to do for cloud-based software. However, what they don't tell you is that cherry-picking commits from master into old release branches is way more error-prone in trunk-based development than it is if you use feature branches. Let me show you why. In every tutorial that you've ever watched about trunk-based development, or Gitflow for that matter, they always show us a bug fix as a single commit, as though every bug was trivial. But we all know that most of the bugs that get past the pipeline and into production are definitely not trivial. So let's walk through an example of a non-trivial bug that has to get fixed in multiple releases of software. Suppose a car manufacturer updated their collision avoidance system 4 times in the last 10 years as cars got more sensors. And now they discover a serious bug that exists in all 4 versions. Let's say they discovered that there was a race condition involving half a dozen threads. To fix this bug, you need to add some synchronization logic in half a dozen threads. In Gitflow, you would do these changes on a branch like this. You need to change different logic in various places in half a dozen threads, then change the unit tests for half a dozen threads, then write new integration tests for this race condition, because obviously those tests never existed. So how would you do that? You change the first thread and its unit tests, you debug it from your IDE till the unit tests all pass, and you commit those changes. You repeat that for half a dozen threads, committing after each thread's unit tests pass. That's 6 commits so far already. So now you write a few new integration tests to actually test this race condition, and you commit those one at a time till the pipeline thoroughly covers this bug. Then you ask for peer review, and you get some comments that you have to address. So you address the comments and you commit once again. So you're up to like 10 commits to fix this one bug. And you have to do this at the same time that other developers are working on unrelated things. Let's say they also have 10 commits each. In Gitflow, everyone would do their development in their own branch, then everyone would squash their 10 commits down to 1 during the merge into trunk. Let's say you did that for your bug fix. Then you just have to cherry pick that one commit from master into each of the 4 release branches. You never have commits in the master branch that say fixed a lint error or addressed review comments. Those commits stay in the feature branch. In master, you've got one squashed commit that just says issue 1271. The master branch history stays very clean. So what did that take us? Each developer had to do a pull to update their local master branch from the origin. Each developer did an update from local master branch into their feature branch. Each developer resolved any conflicts in their local branch and then squash merged their feature branch into one commit on their local master branch. Then each developer pushed their local master branch to origin so the other developers could see their changes. And then you could do one cherry pick from master into each of those 4 release branches to create the patches. How would you fix that same bug using trunk-based development? In trunk-based development, every commit from every developer goes directly into the master branch. And they're all jumbled up, so your 10 bug fix commits aren't sequential anymore. You have to then individually cherry pick all 10 of the commits for this one bug into 4 separate release branches, including those commits that said fixed a lint error and addressed review comments. That's 30 times that the developers have to pull from origin to local master to see everyone else's changes. 30 times they had to potentially resolve conflicts. 30 times they commit their local branch. 30 times they push their local master branch to origin so other developers can see their commit. And finally, you have to do 40 cherry picks without making a mistake instead of 4. And cherry picks are way more error prone than merge conflicts. Git has nice visual merge tools and built-in strategies to help you resolve merge conflicts. But Git has no way of knowing which 40 commits you have to cherry pick, or of detecting that you picked a wrong one or missed one. It doesn't have any tools to help you fix mistakes with cherry picks either. So that right there, 40 cherry picks to get one bug fix into 4 release branches, that's the fatal flaw that makes trunk-based development unsuitable for safety-critical software. Gitflow, with its ability to squash commits before they get to master, is just way lower risk. However, Gitflow has its own fatal flaw. For safety-critical development, Gitflow's feature branching approach is better suited to our needs. Where Gitflow falls apart is how it handles releases and hotfixes. Gitflow is based on the assumption that you only have one supported release. The master branch is where code for the current production version resides, and the develop branch is where code for the next version resides, and there are no other supported versions. When the next version is ready for release, Gitflow says you create a branch off of develop to release from, you fix any bugs found during release testing in that branch, you build the release, and then you merge that branch into both master and develop. Then Gitflow says to delete the release branch, leaving nothing but a tag on the master branch. The release branch is short-lived. Then, if a bug is found in production that can't wait till the next version, Gitflow says to create a hotfix branch off of master, you fix the bug, create the patch release, then merge that branch back into master and develop. And then Gitflow says to delete the hotfix branch, leaving nothing but a tag on master. That hotfix branch is short-lived. The fatal flaw that makes Gitflow unsuitable for safety-critical development is that short-lived release branches do not allow you to provide long-term support for older releases. For example, if today, in 2023, our hypothetical car manufacturer discovered that serious bug, not in the current production version, but in the 2018 release of their collision avoidance system, they would have to create a 2018.01 patch release off of the 2018 release branch, not off of master. And they would have to cherry pick that fix into all prior versions that also had that bug, and make patch releases for all those as well. Short-lived release branches don't allow you to do that. You would have to recreate the 2018 release branch first by branching off of master again at the 2018 tag before you could make a fix to that code base and release a 2018.01. Okay, say you did that. But if you then delete that release branch again, what do you tag as 2018.01? You can't merge that fix back to the head of master. The lines of code that it fixed might have long since been refactored out. So how would you recreate that 2018.01 code base if you had to create a 2018.02 years from now? In order to do that, you need to keep that 2018.01 code base around. You need a long-running 2018 release branch. So for safety-critical development, you want a branched model, but you need long-running release branches. And you want a workflow that enforces the same process rigor for fixes made in past releases as it does for current development, with all the same Git hooks and standards compliance and process enforcement, so that when you make a patch for the past release, you can still demonstrate compliance with the safety standards. So what should a branching model look like for safety-critical software? Well, here's our V model of development, where everything on the right-hand side is derived from and verified against something on the left-hand side. And the branching model comes into play on the right-hand side, from coding onward. And all those different test stages that verify different requirements and specifications, they all execute in different environments. For safety-critical systems, there are different test suites for different stages, and you need verification artifacts produced from each stage for your safety case. To get that, The software has to be compiled differently for different test stages, with instrumentation for branch coverage or instrumentation for profiling. We use emulators and hardware test benches and jigs at different test stages to be able to programmatically inject faults or force error conditions in order to achieve full branch coverage or to prove worst case timing. Fortunately, Git and Mercurial both give you a really nice framework for allowing you to enforce process during coding and during multiple test stages and during release. They let you add hooks to execute actions on commit or merge or push, and to abort the commit or abort the merge or push if the hook fails. Hooks let you enforce prerequisites to a commit or a merge or a push. You can, for example, enforce adherence to the coding standards by rejecting any commit into the feature branch if the code doesn't pass MISRA compliance. You shouldn't have to wait till it's merged into the develop branch and then for a pipeline to fail in order to find out that the source code doesn't even pass static analysis. That code shouldn't have made it into the develop branch in the first place. Static analysis could have been a prerequisite to a commit. Allowing the merge and then having to wait for a pipeline to fail before finding out that code is broken leaves you with a broken build in the integration branch until the developer fixes that code and tries merging it again. So your pipelines end up failing a lot because of broken builds. By making the use of hooks, you can protect the integration branch from broken code. You can push the code to a sandboxed clone of the repo first, called a try repo. You run the pipeline there, and if the pipeline fails, you abort the push to the protected repo. You've tried the pipeline in a safe place, and it failed, so the real integration branch was not broken. Check out Mozilla's documentation for an example of using try repos. And by using different integration branches for the different test stages, you can also break up your pipeline into smaller independent pipelines for doing the specific tests and generating the specific artifacts you need at each stage. And you can make sure that you only merge code into the next stage if it won't break the build. For example, the collision avoidance system probably engages the anti-lock brakes at some point, but you don't want to prevent the latest build of your collision avoidance system from being deployed to target hardware just because the latest build of the anti-lock brake system fails that pipeline. You can deploy your collision avoidance system with an earlier build of the anti-lock brake system because the broken build of the anti-lock brake system was prevented from being merged into the next stage. Just imagine that there's a couple of extra branches between develop and master. So in a safety critical project, you can still deploy code incrementally like you would in Agile. You're just not releasing it to anyone. You're deploying it to different test environments so that you can incrementally get more and more of the full functionality exercised under test. You're building up larger and larger snapshots of the full system. Now you can certainly take that too far and have too many integration branches, but branches are cheap, and using branches gives you more maintainable pipelines. You could certainly do all your testing in one integration branch with one giant multi-stage pipeline, but you're getting no help from your version control system if you do it that way. You'd have one mother of a huge Jenkins file that has to build the source multiple times with different flags, instrumented differently for different targets, and it would have to generate multiple reports and multiple artifacts at multiple stages. When you put that many steps and stages into one pipeline, you start to find that the pipeline gets very fragile, and you end up spending a lot of time maintaining your build system because it's broken a lot. Choosing the right number of test stages depends on the complexity of the system, of course. If you're building a self-driving car, you probably have dozens of different test environments and different test stages and test branches. But having one branch for each formal verification artifact you need to produce is a pretty good starting point. Here's an example of one stage of a test pipeline from software for a medical device. In this test stage, we're proving that the system will execute certain actions within a worst-case time bound. You can't do this with unit tests because you can't calculate timing if you've mocked out most of the system. This test stage needs a full build of the subsystem that's under the time constraint. It needs that build instrumented for profiling and then run in an emulator where you can use white box testing to force the code to execute its worst case. Then you report the number of CPU cycles that it took. This way you can verify that the software continues to meet that timing constraint, build after build, change after change. But you had to do it with a special software build, and you had to run it in a special test environment where you had the capability of controlling the branches that the software executes. As you probably guessed, the safety standards have something to say about our verification process too. 61508 stipulates that 100% coverage must be achieved for all entry points, code branches, and conditional operands, and says any path or condition not tested must be inspected and appropriate explanations given. 62304 stipulates that system test coverage must be accumulated and presented in addition to unit test coverage. And 26262 stipulates that fault injection must be done at both the unit test and integration test stages. So white box testing using emulators and hardware test bench to inject fault and to increase system test coverage. So now let's look at what you have to deliver as a result of all this verification. Let's assume you actually got through all your verification stages and you're ready to submit your product for approval. Now you have to present a safety case to the regulator for approval. A safety case is a structured argument supported by a body of evidence that provides a compelling and valid case that the system is safe for a given application in a given environment. That means the software engineer has to sign and seal all the software engineering works, every artifact, analysis, review, and test result. And with those, you put together your body of evidence. We identified the hazards, we analyzed the hazards, we defined mitigations for each hazard. Those mitigations all appear in the design. The software implements every one of them. The tests verify every one of them, and it meets the required probability of failure for its intended safety integrity level. And I signed and sealed all those artifacts and certify that they were produced in accordance with professional standards of practice. We therefore claim that this system is safe for its intended use. Safety critical systems generally have a long lifetime, 10 or 20 years. Therefore, you are required to have a maintenance plan that documents your procedures for how the software's health will be monitored over its lifetime. How will you know if there are problems with it? How any defects will be addressed, how third-party code updates will be managed, how obsolescence of your development tools will be managed. What are you going to do if the emulator that you used when you built the 2012 version of the collision avoidance system is no longer available when you have to release a patch for it 10 years later? After it's released, all project materials have to be retained for a minimum of 10 years, or longer if the documentation is still in use after 10 years. And finally, you are required to have a decommissioning plan that documents the procedures to be followed at the end of life of the project, including the destruction of any material that can be used by bad actors. So you're probably all thinking, holy crap, that was a lot of work. Well, yeah, but there's reasons for it. The level of risk means there has to be a rigorous approach to development in order to protect the public from harm. Therefore, development is geared towards safety, not speed. The methodology is focused on every step resulting in a formal artifact, which is derived from and verified against another artifact, which is the exact opposite of Agile. Every part of the development process has to comply with some very strict standards. And there is no open source tech stack that gets you most of the way done. The fact that it doesn't run in the cloud and does need long-term support means that some common practices like Gitflow and trunk-based development and CI and CD just don't work here. And finally, if there is harm to the public, that usually leads to lawsuits. So unless you've got $2.5 billion to spare, you've got to be very diligent during its development. So there you have it, Safety Critical Software Development 101 and Gitflow's fatal flaw. I hope that was interesting, and hopefully you now feel comfortable voicing an informed opinion of your own. Do we do the same job? I'll hand it back to Vivian now for questions.